Okay, so what's a package manager? Do people, raise your hand if you think you're familiar with what a package manager does. Oh, okay, so like half the audience. Spack's a package manager. We often get the question of, why don't you just use AutoTools? Why don't you just use CMake with Spack? Why are you building this new thing? And the answer is it doesn't replace those project level build systems. It drives them. And so if you think about the way that build systems work, there's low-level build systems that you're probably familiar with, like Make and Ninja. These handle dependencies among different commands and different files within a single build. And so these are managing things like, I need this compiler to build this object file. I take that object file and these other object files and use them to make an executable. And that's fine. These tools have been around for a really long time and they're extremely useful. High-level build systems like CMake and AutoTools are built on top of those. And so if you think about what these things do, CMake and AutoTools both generate Make files, Ninja files, other types of files that like CMake generates, I think, Visual Studio projects too. These mostly handle the complexity around simplifying the syntax in the Make file. Because if you have a large project with lots of different targets, lots of different libraries, lots of different source files, your Make file can get fairly complicated. And also handling library abstractions across machines. So one of the advantages that you get with CMake and AutoTools is that every different operating system has a slightly different way of building things like shared libraries. So macOS does it differently from Linux. Windows does it differently from both. CMake and AutoTools abstract that and make it so that you basically just say, here are the sources that are going to go into libraries and it automates the rest for you. They do a lot more than that, but I think the library abstractions and the fact that these are focused on a single project is really the key difference. When you build something with CMake or AutoTools, you might say build with some other project. And that means you're going to take that project to dependency. It needs that library to build. And so what Spack is really doing is managing those connections between projects. If this thing that's built with CMake or AutoTools needs a glib or ECF5 to build, Spack is coordinating that and managing the relationships between those packages. It's saying, okay, I know that you want to install Nalu. I know it needs HDF5. And I'm going to pick some versions for those things and pick how HDF5 should be configured so that it meets all of the requirements of Nalu. So it's really managing this sort of version selection problem and the coordination of lots of builds in a directed acyclic graph. So static versus shared libraries, I think most people are familiar with this. But when you actually write package files in Spack, you're sort of controlling these build systems and telling them to build different types of binaries. And so static libraries are things like libfoo.a. These are archives of O files. They really are just they're just zipped up object files. And the linker will take in a .a file and include the parts of it that it needs in the final executable. So you get one file, it's self-contained, it includes all of its dependencies, and it plops that down on the disk. And you can go and run that lots of different places because it includes all of its dependencies, provided it's binary compatible with your OS. Shared libraries are used very much by the operating system. It's becoming extremely hard to build all static binaries, so you generally have to build some things shared, so things that require pthread support on modern machines, for example. A lot of MPI implementations just won't build static. And so, this is a reality that we have to deal with. I think HPC's managed to escape it for a while, but on modern HPC machines, people are starting to use shared libraries a lot more. Essentially, instead of including all the dependencies into one executable, what this is doing is it's dropping a bunch of different files on your disk. So you may have one package like Nalu that has an executable. You may have another package that has a bunch of .so files. And Nalu needs to know where to find those libraries so that they can execute code at runtime. So there's this runtime, build time separation. And so there are two main ways that people use shared libraries. They build the things, and then they will either make it so that you have to set LD library path at runtime. LD library path is an environment variable. It's a search path that tells you where to look for shared libraries. Or you can embed paths in executables and libraries. And so one of the things, and we'll talk about this in more detail later, that Spack does that I think at least was new at the time and still remains pretty new compared to how module systems are run, is we use rpath extensively. And we do that because we want all of the executables that you build with Spack to know where to find their dependencies. We don't want the user to have to configure LD library path because A, it's a burden on them, and B, they probably have a lot of different programs that they want to run that may use incompatible versions of different libraries. So if you set LD library path globally in the user environment, it's very hard to use a lot of different tools. And the user ends up in basically LD library path hell. So we don't like LD library path. A lot of module systems will set LD library path and rely on that at runtime. You can combine that with what Spack does. In fact, we generate modules. But Spack is designed so that if you do just find something in a directory, you can run it. API and ABI compatibility. Who knows the difference between these two things? Raise your hand if you think you do. Okay, Greg does. Awesome. Okay, and a few people with Greg. Okay, so the application programming interface is something you're probably used to hearing about. It's basically source compatibility between two libraries. If a library exposes an API, it means that you can write source code that looks a certain way, that makes certain types of calls and passes certain types of arguments to that library, and that if you run that with another library that's API compatible, they should both build. They should be fine. You may need to recompile to use a new version of that other library. API compatibility is something a little stronger. The API is basically the calling conventions at the binary level on your machine. So it's things like how are arguments passed on your architecture. It's things like the sizes of different types. How are different structs actually laid out by the compiler. And this is where things get really tricky, especially in HPC, because there are lots of libraries that are API compatible, like MPI, that are not ABI compatible. And so we often get users who will build with one MPI, they'll try to run, they'll load another MPI, and their code will explode. Or they'll run with one BLAS, they'll build with one BLAS, they'll run with another, and their code will explode. Same thing across compilers. This is a constant problem. And so if you don't know exactly which dependencies you built with, it's pretty easy to run into ABI compatibility problems. So if you're using LD library path, that's a frequent issue. C++ is really bad about this too. So C++ has no ABI standard, and libraries often, especially header-only libraries like Boost, will change the type signatures for things in the libraries across different versions. So you may build an application with one version of Boost and then build a dependent package with another version of Boost. And then the function calls between them are no longer compatible because the same type, like auto pointer, in one version is not the same size as it was when you built the original library. So this is a frequent problem. And so yeah, there are lots of ABI incompatible libraries. Spack is very conservative about this, and we try to make sure that when you build something, you're getting exactly the libraries. By the time you run something that you built, you're getting the exact libraries that you built with. We don't want you to have to think about build issues at runtime. There's three major build systems to be aware of when writing Spack packages. So there's make. This is usually GNU make. I think most people are familiar with make. There's AutoTools and there's CMake, and I will talk about the details of those. So make files. Typically, if you download a project and see a make file in the root directory, what you're going to have to do is edit that make file to work for your platform, do some magic in there, and then maybe pass it a prefix where it's installed. And there's no configuration options on the command line, at least. You typically have to edit files. And there are some environment variables that you can set to get things built, but they're not that consistent. These are the environment variables you're supposed to use in a make file. I've seen HPC make files with really horrible and weird environment variables that make no sense, that are not the implicit ones. And so if you just set these without actually reading the make file, you may not actually build your code right. And so there's sort of a package-specific aspect to configuring things with make files. It's not very standardized. If you're building a Spack package that edits make files, you're essentially automating this process of editing the make file and then invoking make. And we'll talk about that in the packaging section. For AutoTools, there's three parts of AutoTools. It adds this extra step where you say configure and you say -- prefix equals path to where you want to install. And this differs by tool. Ill-behaved tools like Tau, I think, have like dash prefix instead of dash prefix. And so there are certain things where some tools will deviate from AutoTools in small, annoying ways. So you have to know things like that. The configure step in general, though, generates a set of make files. And then you say make with what is configured, and you say make install to get it into the prefix that you asked. There are some relatively standard configure options for AutoTools packages, at least if they're written well, and that's not always the case. You pass the prefix, that's fairly common. There's often ways to specify your dependencies. Sometimes this is passing the path to dependencies, sometimes you have to pass the libraries explicitly, sometimes you have to tell it where the headers are, things like that. These are all things you have to do on the command line. So it's a little more consistent, but not too much more. And you may want to enable and disable different features. All of these are basically arguments to configure that control how the make files are generated. And then with a little bit of a stronger expectation than you can with make files, you can use these standard environment variables to control the behavior a lot of tools. So you can set DC, CXX, SC, things like that in the environment to control how the configure script is or how the make files are actually. And usually the other tools build will respect these. For CMake, it's also pretty simple, or it's similar. The typical build incantation is you make a directory, you go into that build directory, so you're building out of source most of the time with CMake. Whereas with AutoTools, you can do that in some cases, but we typically don't, at least in Spack. You can invoke CMake with arguments. That is pretty much like invoking configure. It's just that it's an external executable instead of a script that's included with the package. You run make and you run make install. The configure options, though they have different syntax, are pretty similar to what you would do for AutoTools. So you can say where to install. You can say there are usually options for specifying your dependencies, options for enabling different features. There are some standard ones. And there are standard things you can pass on the command line to control the compiler, the flags, and things. And so these are some of the common options for CMake. CMake C compiler instead of just CC. CMake C compiler. And this is all available in the documentation, but this is just good stuff to be familiar in general, because if you get an HPC stack and you have to build it, this is most of the build systems you're going to. So, and I think the takeaway here is this is all the stuff that Spack is automating for you. Essentially, you're building a package that describes the recipe for how to do these things, and then Spack automates the process of stitching that together with lots and lots of dependencies. All right, so that's it for the build and linking basics. Any questions on that stuff? Yep. Oh. Yes.
Just wondering about all the tools that are out there in the real world outside of HPC, like the Java build tools, Python build tools.
So I would say, for Python, we have special packages with Python support. So yeah, we do support the Python ecosystem. We actually have a lot of our packages too. I didn't mention the language-specific build systems because a lot of those are really handled by superclasses in Spack. So if you write a package recipe, you can generally just use our built-in support for those things. And that's actually true for most of these too. Greg will talk a little bit about that. But yeah, we do support those things. We don't have, I wouldn't say, a very extensive Java ecosystem at this point. But I mean, that's something that we could work on. It's a little bit of a different install model because generally when you distribute Java, it's not, I mean, you may not even have to compile it, right? It comes as jar files, and there's a whole different set of build tools there. But yeah, if that's something you're interested in, I'd like to talk about how we could support it. Yep.
Do you find that there are very many HPC systems that deal with anything beyond AutoTools or CMake? For example, Ninja or Cotire?
So we see Ninja a lot because people will just use it to, they'll generate Ninja from their CMake build, right? And so, I mean, it's almost like you get Ninja for free with CMake.
Isn't that an external application as well?
Yes, and so if you use CMake with Ninja support, you have to install Ninja first. Right. But that's something Spack manages for you, right? So,
so in the Spack.
Yeah, Ninja's in Spack. If you want to install a CMake package that uses Ninja, it'll install Ninja for you.
Do you find many users do it in HPC?
I haven't seen that so much. I know that Ninja can be a lot faster than Make, and so I've seen users who want really big build systems to build fast use Ninja. So I mean, I think it's pretty cool. It's a little lower level than what we generally care about in Spack. It's definitely something we can automate, and I mean, support it. I haven't gotten down into the details of it. But yeah, we do see other builds. I mean, we see a lot of Python. We see, we see Julia stuff. We see R a lot. We even see a lot of Perl. There's a lot of Perl packages in Spack. So yeah, you'll see in the packaging section that really this is sort of an overview to give you an idea of what Spack's automating. But really in a Spack package, it's written in pure Python. So you can do anything, right? If you can write a program for it, you can do it in a Spack package. It may be painful, and we may want to integrate support in the Spack core for it, but you can write it. Other questions? Nope. Okay. You want to use your machine or this one? Let's just use this one. Yeah. Okay. All right.
Still on slides for a bit.
Yeah. All right. Cool. Do you want a terminal?
Eventually.
Okay. I think I have it. Let me just make sure you get it. Yes, a terminal window. And do you have a VM? No? Okay, I'll get you one. Okay. All right, cool. All right, so Greg's going to do.
All right. So, a lot of background. Now we're going to talk about how we actually use Spack to install a package on the system. So, Todd mentioned there's a lot of different ways we can configure any of these packages, and thank you. And we need a way to specify, think of that as the entire build space. We need a way to specify which point in that space we're talking about. And so that's what Spec Syntax provides us. The simplest spec is just a package name. I want to install MPI leaks. That's an MPI debugging tool. I don't care anything else about it. I just want MPI leaks. I want it to run. You can say Spack install MPI leaks. Spack will figure out all of the defaults for all of the options. It'll build all of your dependencies. Then it'll build MPI leaks, and you can run MPI leaks. But sometimes we care a little bit more what we're running. So we can use the @sigil to specify versions. We can also specify version ranges with a colon using a syntax kind of like Python array slicing, except that it's inclusive on the upper end. We can use the %sigil to specify the compiler. And you can see that within that, we have the @sigil again to say which compiler version. You could also just say %GCC. You don't care what version of it, but you care that it's GCC. You can have build options, turn things on and off, turn on debugging, turn on threads, turn off MPI. You can add arbitrary compiler flags into the build. We'll talk a little bit more about this later, but Spack includes a compiler wrapper, so we have an easy place where we can inject flags into the build. We can specify the operating system and target. This is primarily for machines like the Cray machines where you have cross-compile environments. You could want to build something for the front-end node or build it for the compute nodes. And this whole thing is telescoping, recursive. If you can say it about the package at the top level, you can say it about one of the dependencies. You use the *sigil. You can read that as depends on. You put the package name of something that it depends on, and then you can say all the same things. And you could combine these and say, okay, I want to build MPI leaks with GCC 473, but mpitch has a bug with 473, so build mpitch with 493. And generally, Spack will try to use the same compiler across the entire DAG, but if you're really specific and give it 2 different compilers, it'll say, all right, you told me to use 2 different compilers, I trust you, here you are. Now, if those compilers aren't API compatible, you're out of luck. So Spec List shows you what packages are available. This slide is very old. There are only 303 packages in it. There's about 2,900 in the latest release and about 3,200 on the tip of develop. Spack Find will show you what is installed. So here we can see an example of a bunch of packages installed with Spack. And you'll notice that here we've got 2 packages that look from this view identical. Right? We're not looking at everything about these. We can assume there's something else about those that's different, and I'll get back to that in a second. Todd also mentioned we set up the binaries to work regardless of the user's environment using RPath. So this is why, right? We have a bunch of different versions of different things. We've got, we've got 2 different dynams here. We've got 2 different adeptutils. We've got a 3rd adeptutils there. We don't want users to have to keep track of that. And so we set up the RPath so that they find these automatically. We also generate module files, which you can use to navigate these, but you don't have to use them. They're in no way required to get these packages to work. So I mentioned these 2 different versions of adeptutils. What's different about them? Well, if you zoom in a little bit, you can use the Spack Find -D for dependency information and -L to show the hashes. And we can see here think the next slide highlights it. Yeah, we can see here, here's our two different adept utils that look the same. And it's because they were built with different versions of Boost. That telescoping syntax, you could have specified different versions of Boost on the command line. And then the other key thing for sort of basic usage of Spack is we manage the installed compilers. So we automatically detect compilers in your path variable on most systems. On Cray systems, we use module avail to find the compilers. And we dump that to a YAML file. You can add things to it manually. You can create Franken compilers that use Clang for C and C++ and G-Fortran for Fortran, for example. We'll give an example of that in the configuration section later. And you can manually add to the file, and you can manually say, hey, Spack compiler find, give it a path to some compiler that you've installed. So, any questions on that before we dive in for a little hands-on? Yes?
You mentioned you can specify different architectures for the target,
Yep.
for the processor. Can you do something equivalent, or is it handled some other way to do that for different fabric architectures?
So the fabrics are generally handled as variants on as build options on the packages that care about them, because it's not something that's universal. We've talked about maybe moving that into the architecture, but we haven't really seen any need to so far. So if you look at any of the MPI packages, they generally have a multi-valued variant, which we'll talk about more what exactly that means. But basically the option to specify which fabrics you care about. Any other questions? All right, so let's do some hands-on. And seem to have lost my terminal window that I was going to bring forward. There we go, and then I'll need.
I think it's not me.
Yeah.
Is that right?
Full screen sometimes.
Yeah. Let me get the system first. Is it big enough?
Bigger.
Yeah, probably bigger.
Mario, is that big enough to read from the back?
Yeah.
Okay.
Okay, and then I guess, can we minimize this on the screen?
Yeah.
Okay. Oh yeah, so I guess, I wish we could write that somewhere. If you want to find this page, go to bit.ly/spec-tutorial. There's a short link for it. Is there a, I'll like write it on the chalkboard somewhere. We'll see this. Yeah. Can you read that? I'll write it over there too.
All right.
And then you can find the script at this site.
So now logged into one of the VMs. Everyone on one of the VMs that Todd was giving out earlier, or on the Docker container for the tutorial. All right, so the first thing we're going to do is we're going to clone Spack. So git clone, HTTPS, etc., github.com/spack/spack. And Spack just works out of the box. If we reached into that directory and called the Spack binary, we could install things right now. But instead of adding it to our path, we're going to source the setup script because that allows us to do a couple of nice command line integration features later in the tutorial. So we're going to source, so we're going to cd into the Spack directory. And actually, we're going to check out the release branch. That's also important. Git checkout releases/v0.12. And the reason we do that is we have pre-built binaries for a lot of this tutorial, so we don't have to wait for things. And to make sure that we have exactly the right hashes to find those binaries, we need to be on the release branch. Now we'll source the setup script, and that'll put Spack in our path. So from here, we can start using Spack, Spec List, get a lot of output. So maybe it's more useful to narrow that down somewhat. Spec List py-. That'll give us all of the Python packages. They're all prefixed py-. Now that's actually still a lot. Maybe we want to see YAML readers. So Spec List YAML. And you see a few different YAML readers. In general, for Spec List, think of it like if you're using the command, or if you're using a shell, star, and what you typed, and then star, it's going to find anything with that string anywhere in it. So now let's install something. Spack installs zlib. Why zlib? Because it installs very, very quickly. Spack takes a second to run. The first time you run it, it generates some information that it caches for you. And here we go. We've installed zlib. Spack can install from binaries or from source. The general use case is typically from source, but for the rest of the tutorial, we're going to install everything from binaries so we don't have to wait for build times. So
when you mean binaries, are these like RPMs or are these some format specific to Spack?
These are a format specific to Spack. The reason we do that is they have to be relocatable.
Okay.
So the directory that they're built in is not necessarily the directory that they end up in, and we have paths embedded in them for the locations of their dependencies. And so we actually relocate the binaries as part of that. And you'll see on some of the things that we build, you'll see output saying relocating from.
So does this provide any additional features on top of the typical relocatable RPMs?
So I am not an expert in RPM, but it also allows us to use the Spack specs as the sorting. So we briefly tried to generate RPMs from Spack, and that did not go very well because their model of what a dependency is so different from ours, and it was very hard to create a naming scheme that could get enough dependency information.
Okay.
So I'll bring this to the top of the screen. So now we're going to say Spack mirror add, we'll call it tutorial, and it's located in /mirror on these VMs. And that's just telling us, hey, look for binaries and source in this location. And then we'll say Spack GPG trust. So the binaries, if I can type properly, that would help. The binaries are all signed with GPG. And what we've just done is we've trusted the GPG key that I used when I created these binaries. So now we can install lots of things quickly. We can say Spack install zlib. And remember, we use the %sign for compilers, and we can say clang. We don't care what version of either. The first time you install from a mirror, it goes out and it reads a lot of files from the mirror. But after that, it won't have to do all of this. It'll just have to do this part. So if you look at the bottom here, you can see that this was installed in a different location, right? It's got the compiler in there. It's got this hash. And this lets us keep all of these installations around at the same time. Yep.
So are these mirrors similar to the typical mirrors that you have with like Ubuntu or like Red Hat, where like different contributors can set up their own mirrors?
Yes, that's the idea.
How do I see what's in a mirror?
That's build cache find.
So the mirrors were initially designed as source mirrors. And so generally the commands to handle the binaries in a mirror are Spack build cache something.
Okay.
And the commands to handle the source in a mirror are Spack mirror.
Is the user's configuration for Spack, like things like setting up his mirrors, stored in like a local config file?
Yes, and
Is there a system-wide config file you can override?
yeah, and we have an entire section on configurations after the morning break.
I will point out, we don't currently have a public mirror. So Spack is mostly built open source right now. It's used to component themselves. What we're going to talk about tomorrow is some of the efforts that we're undergoing to make like a mirror for E4S and some of these other software distributions that we're talking about.
Yeah.
But we're using this mirror in the image for the tutorial so that you don't have to wait for the source build.
Yeah. So now if we want to install a different version of zlib, we might know what the versions for zlib are, but we might not. So we can say Spack versions zlib, and that'll give us the versions that Spack knows about first. We have checksums for those. We know we can download them safely. And then all of the other versions that it can find on zlib's website. And so we could install any of these. We'll get a warning if we try to install one of the ones that we don't have a checksum for, saying, this isn't safe, do you want to keep going? So let's install a version we do know about. Spack install zlib. The @sigil is versions. And spacing around the sigils doesn't matter, except for when you're using like a key equals value type syntax. So let's install version 128. And we can also install with a different compiler version. So we can say we want the compiler to be at the GCC compiler at version 4.7. And you can see for both of these, it went and grabbed it from the mirror. And you can see at the bottom here, we mentioned relocating.
I was trying Spack versions on a couple of other packages,
Uh-huh.
and I see something called state versions already checksummed and remote versions not yet checksummed. So what are they?
So we'll talk a little more about this when we do the packaging, but when you create a Spack package, you put versions in the package file and checksums for those. And when Spack downloads the source, it checks the checksum to make sure that you're actually getting the source you want. The remote versions are ones that we don't have the source for, or the checksum for. We can still download it and build from it, but we don't have that reassurance that someone isn't using a man-in-the-middle attack to give you something nasty.
That actually takes the URL of the tarball and goes and scrapes the web page for this. So it's telling you what's available. You may see new ones pop up there depending on what's been posted to the website.
Yeah.
There's another command called Spack checksum that'll go and automatically download the tarballs for you and spit out the versions of the checksum.
So we mentioned using compiler flags as well in the spec syntax. We can do that. Zlib at 1.2.8. And then here's where spaces matter. Obviously, we need a space before the CPP flags. So we'll set the C preprocessor flags to optimize both C and C++. Although obviously Zlib is pure C, it doesn't really matter. So now we've installed a few things. Let's look at what we've done. Spack find will show us what we've installed. We've installed 5 different configurations of Zlib. And we can see at the bottom here, 2 of those configurations look identical from this view, right? We're only seeing the architecture, the compiler, package name and version, and these 2 share those. But the -F flag will show compiler flags, L will show hashes, and we can see the reason those 2 versions are different is we said we wanted that optimized version. So we've touched a little bit on the hashes. The hashes are actually generally what Spack is considering internally. If the hash matches, they're the same package. If it doesn't, they're not. Let's install something with a dependency. Let's say Spack installed. I'll clear this to the top of the screen. Spack install TCL. Why TCL? Because it depends on Zlib and nothing else, so it's convenient. And we can see the default Zlib was already installed when we ran Spack install Zlib near the beginning. So we didn't need to install that now. We install Tickle, and we're good. But we can also request specific dependencies. We can say Spack install TCL depends on Zlib at 1.2.8 built with Clang. Now, this is specifically saying we want Zlib to be built with Clang. Now, we hadn't built Zlib 1.2.8 with Clang before, so this time we had to go out and build Zlib first. And then we built TCL against that. And notice that because we didn't say what compiler to build TCL with, we got Clang also, because Spack will try to keep things uniform across the entire dependency DAG. We can also refer to things by their hash on the command line. So remember earlier we ran Spack find -lf, and you can see that this optimized version of Zlib that we built has the hash that starts 64MN. So if we want to build Tickle with that optimized Zlib, we can now say Spack install TCL depends on, we use slash sigil for hashes, and we can say 64MN. And really, you just have to put enough of the hash that it's unique. There's nothing special about 4 characters. It's just usually enough. So now that Zlib is already installed, and we build TCL against it. Now, if we want to look at what we've installed, Spack find -lf, and then there's also the D flag will show us dependency information. So we get a tree view of the dependencies of each thing. Obviously, these trees are pretty simple. And we can see, you know, here's our TCL built with optimized zlib, TCL built with GCC, TCL built with Clang, way at the top where I can't point to it. And then some versions of zlib as well. So let's install something a little more complicated. Spack install HDF5. And you can see this has a few more dependencies.
Is there a stock command to generate the DAG?
Yes. So if we do spec HDF5, you can see what it is going to install when you install HDF5. If you do spec-I, it will also show you which of those things are already installed. In this case, all of them, because we just installed it. But if one of them were not installed, there would be a little minus there.
Use that graph.
We do that.
Okay, we'll be.
So we haven't talked much about build options for the individual package. You know, how do you drive the package's build system to build it in all of the different ways that its maintainers want you to build it? Yes.
So here you use the hash to find the zlib you wanted, but if you had specified the same variants that zlib had been built with, the concretizer should have matched the name, right?
Yes, assuming you haven't changed your configuration files in between. If you've gone in and changed your preferences in between, then that'll change the defaults that it finds. So right now, when we do defaults, we're getting GCC. Later, we'll show you how to set it up so that your default is Intel or your default is Clang. So the hash is the safest way to get a specific thing. But yes, the concretizer is deterministic in that way. So HDF5 can be built parallel or serial. We can turn on or off the MPI dependency for HDF5. So let's say Spack install HDF5 without MPI. Much simpler. You can see most of the HDF5 dependencies were actually coming through MPI. There we go. We might also want HDF5 with a different MPI implementation. They're interchangeable. So we could say Spack install, or I should say they're interchangeable at the source level, but we can't just swap them in at runtime, so we have to build independently. And we'll say plus HL, that's the high-level interface. I'm turning this on for something that will use it later. Plus MPI. And I want it to depend on mpitch. And if we do a Spack find-LDF, now we can see all the different things that got installed as part of this. And if I do a Spack find-LDF HDF5, we'll see just those three. The default one with OpenMPI, no MPI, and with mpitch. So all of this that we've seen is a tree representation of the dependencies. But that's not necessarily accurate. And you can see that zlib shows up in different places in these three trees. And the reason is that dependencies are actually a directed acyclic graph, and that's what's going on under the hood. So if we say Spack graph, and we'll just give it the same spec we just built, and we get this nice little ASCII art of the dependencies.
Can you get a version information of those dependencies as well?
Not on the ASCII version of the command. I think you get some more information when you have it generate dot, which we'll show later. So the Spack find -d output that we were just looking at, I'll bring this back up, doesn't actually show all of the things that were built, right? If you may or may not have noticed as it flew past, but we were building tech info as part of our build of mpitch. And that's because of different dependency types. Tech info is a build dependency, but it's not a link or run dependency. So we don't need to know about it when we're knowing, okay, what is this HDF5? But we needed it to build. And so you'll see these things are not part of this tree, but they were built along with the package. So HDF5 is a little more complicated, but it's not that bad. Most of us could get HDF5 installed manually reasonably quickly. So let's do something a little harder. Spack install Trilinos. And I like picking on Trilinos because their build system is really complicated. It's really hard to get all of their dependencies built. And their code is useful enough that we all use it anyway. So this will go out and download binaries for all of these things. I've heard an estimate that if you give building Trilinos to a new programmer as a task, it'll take them 2 to 3 weeks. Using Spack, building from source, it'll take about 3 hours. That's very dependent on exactly what machine you're building on, obviously, but that's what I got when I made the binary cache. And here it's going to be about 2 or 3 minutes total downloading it from binary.
So you can refute or verify any of the claims about Trilinos. Or he can just repeat the comment.
And you can see with longer packages, this relocation step, right, we're going through changing all the R paths in Trilinos to point to the new locations of the dependencies.
So one of the major things with Trilinos is being able to turn on and off packages, right?
Yeah.
In the do configure script. Can you quickly demo how I would do that? There's all sorts of Petra and
yeah. So
did you see that install failed though?
yeah, we'll talk about that in a second. So
okay.
Spack info Trilinos.
Specs for all of these to say
yeah.
true or false.
Yeah. You've got some things, right, the build type, here's these different options, but all of these true false ones you can turn off with a tilde, on with a plus.
Cool. Trilinos has a lot of
yeah.
So like it would be,
and everybody turns them on and off in their own way.
well,
Which
yeah.
is why this
so,
is important.
Yeah. It might be nice one day to have separate packages for different pieces of Trilinos, but that's another discussion.
Yeah.
Right now, it's like we can get a lot of unnecessary installs of Trilinos because different programs will have slightly different configurations and they're all lumped into one package, so the reuse is hard.
Yep.
So someone mentioned cannot open configuration file. Seemed like this errored. This didn't actually error. It successfully installed Trilinos. The reason it had a problem is that OpenMPI is currently the only package that I know of, actually, but there may be others that are not well relocatable because they hard code a string with the location that they're built to into the package. And we don't have a way of relocating that yet. So this brings us to the next thing I want to do for the tutorial, which is Spack install Tralinos. We're going to turn on HDF5, tell it to build with HDF5. And you can see this HDF5 spec at the end looks a lot like what we built earlier. In fact, it is going to build what we built earlier. Now, what I want to highlight here is that Tralinos and its dependencies depend on MPI in many different ways. Tralinos can depend on MPI, Mat.io can depend on MPI, lots of these packages. When we build with Spack, we will guarantee that there's only one MPI provider in the entire dependency graph. So not only do we resolve the dependencies, but we have a concept of a virtual dependency for things like MPI that are abstract interfaces. And we will make sure that only a single provider of an abstract interface is in the graph at any given time.
Is that based on whether the package that has the dependency explicitly requires the abstract interface, or whether the dependency provides the abstract interface?
Whether the dependency provides the abstract interface.
Okay, I have a problem with that, but
So some dependencies some packages optionally provide an interface.
okay.
And they only have to be unified if they are, in fact, providing that interface at the moment. Say, Intel Parallel Studio may or may not provide MPI depending on which options you give it. Does that answer your question?
Yeah, so two packages provide, let's say theoretically they provide the LA pack.
Yeah.
But you don't actually use LAPACK, but you need to use something else from both of those. Would that be a problem?
Then you would need to have variants for them where you could turn off LAPACK.
Okay, so that would be like we would have to rewrite the ESSL to turn off its providing of LAPACK, for instance. Yeah. Okay.
And maybe that would be a convenient fiction because it wouldn't actually change what was there, but you're just promising not to use LAPACK then.
Right.
So we can now see Spack find -d Tralinos. We have these two different installations of Tralinos, and the difference is mpitch here, OpenMPI here. Just for fun, we can try Spack graph Tralinos. And even with the nice colors that we get, the ASCII graph can get a little tricky to follow. So we also have the option to create graphs with dot, and then you can create a PDF, but we actually haven't put dot on these VMs, so we're not going to demonstrate it. Any questions about the spec syntax, installing packages? All right. Of course, the next thing to do after installing packages is what do we do when we installed something we either don't need anymore or actually didn't want in the first place? So at the beginning, we installed 3 versions of TCL and 3 configurations of TCL and 6 configurations of zlib. And that's probably a little bit overkill. So we can say Spack uninstall We use the same spec syntax to specify them. Spack uninstall zlib %gcc at version 4.7. Yes. And the syntax is used slightly differently by uninstall than by install. When we install, it fills in all the defaults and then gives us exactly that. When we uninstall, it says, do I have anything that satisfies this? If it has anything of which that is true, well, if it has exactly one, it will uninstall it. If it has more than one, it will ask us to be more specific. So now we can say spack find-lf zlib. We're down to 5 of them. And now we can say, okay, we don't want an old version of zlib with Clang. We only want the newest version with Clang. So spack uninstall zlib /i426. Notice when I used a hash earlier, I didn't put the package name in front of it. Actually, I'm gonna. I just brought that up to the top of the screen. When I used the hash earlier, I didn't put the package name in front of it. Now I have it there. That's exactly the same. You can put a partial spec and then the hash. You can put just the hash. It still goes and gets the thing that was that hash. And Spack says, no, we can't uninstall that. There are packages that depend on it. So now we've got 3 options. We can either leave it there. We can do uninstall-f, which says, really, really uninstall this. I promise I don't care if it breaks anything else. Or we can say -R, capital R, or -- dependence to say, uninstall everything that's using it too. And that's what we're going to do here. So we're going to uninstall 2 packages now. There we go. I mentioned earlier that we need to be specific. If we say we've installed Trilinos twice, if I say uninstall Trilinos, Spack says, well, I've got 2 of those. Which did you mean? And again, we've got 3 options. We can either give up. We can say -A or -- all, say just get rid of all of them. Or we can be more specific. In this case, I'll say /RLSR is the version of Trilinos that I want to uninstall. There's a couple of things with Spack find that I want to go over real quick that we haven't tried already. So one thing is anonymous specs. Spack find depends on mpitch. We call these anonymous specs because there's no package name here, right? We haven't specified a package, we've just specified a constraint on that package. And so here's everything that we've built that depends on mpitch. Or spack find CPP flags equals -03. There's everything that we built in this optimized way. And it turns out it was just that one at the beginning. Couple other options. We can do spack find -x, which gives us everything that we installed explicitly. Capital X gives us all the things that were installed implicitly as dependents of something we installed. And we can do -p, which gives us the paths. And so I've done that only for the explicit things, but that's where each of these things were installed to. Any questions on that? All right. So now managing compilers. We've used 3 compilers so far. Turns out there were 4 available to us. Spack compilers is just an alias for Spec Compiler List. The same thing, tells us which compilers we have available. Now, if we want to build with something newer, well, we can build our own compiler. So Spack install GCC at 720. And if we weren't using binaries, now we would wait here for an hour and a half, depending on the system we're on. GCC is a little bit big.
Is parallelization of build handled automatically? Like make jobs?
Make jobs is automatically put to the lower of the number of threads on the machine or 16. Because you don't really get any benefit going beyond 16, and we were angering people by taking over entire nodes with make-J256.
We could also like expire your entire Intel compiler license with one Spack install. We were using number of cores on the node as the default. So that's why we capped it.
We have plans to add node-level parallelism where we can farm out the DAG and build up, but that hasn't been implemented yet. So here we've got our GCC. Important to note, we've just installed GCC. We have not told Spack to use GCC. So if we say Spack find-p, actually, we could use find-p, but we could also say location-i GCC, and we can see where it was installed to. And now we can say Spack compiler find or add their synonyms, Spack location-i GCC at 720. And now we've added it to the compiler config, and now Spack will recognize it as a compiler it can build with. And now the next thing we're going to do, well, actually, so we can say Spack compilers. We'll see it show up. Since the default preferences are the newest version of GCC, if we say Spack zlib, by default, we'll now build with that one. But the first thing we're actually going to do is remove it again so that it doesn't interfere with the next section of the hands-on. So make sure to do Spack compiler remove GCC at 7.2.0 because that will cause you to try to build from source with that compiler instead of getting the binaries built with the older compiler in the next segment of the hands-on sessions. So that's it for the basic usage section. Any questions on anything that I've covered here so far before we go on to talk about the internal model of Spack a bit?
By doing this, we have just stored the Spack environment that GCC 720 is a compiler that you care about. Is that right?
So first we told it, there's a compiler in this path, right? This we saw earlier evaluates to a path. We told it, go look in this path for a compiler, and it found it, added it to our configuration. So now it's a compiler that's available for us to use.
So can we do something similar, like for higher level, let's say tools like, for instance, like an OpenSHMEM compiler or an API compiler?
So for an MPI compiler, that's not how you would use it in Spack. The MPI compiler wrappers are pretty thin, and so most of the time, well, there's a couple different ways you can build with MPI and Spack, but basically those get added to environment variables by the packages themselves when you're building and get injected into the build that way. The compilers here are just your C, C++, Fortran compilers. The other compiled languages are handled as packages in Spack that you can depend on. And we aim to eventually handle these more like the other ones. Other external things that you want to build against that were on the system, you can configure to use, but we'll talk about that in the configuration section later.
I think the key detail there is MPI is modeled as a dependency, but that doesn't mean that you can't use the MPI compilers to build your package in the rest.
Yeah.
So there's a whole, if you look in the documentation site, there's a section in the packaging guide on how to use MPI in Spack.
Yeah.
And it basically says what you need to do if you want your build to treat MPI as a library, as a compiler, as a whatever.
We'll talk about that some in the advanced packaging section later.
So in order to add Intel compiler, for example, has
Yeah.
a slightly different internal organization of directory. What does it have?
Yes and no. Yes, it will find it. Depending on how you have your Intel compiler configured, you may need to manually add an extra RPath argument, and we'll talk about that in the configuration section because the Intel compiler is not always good about finding its own libraries. We'll talk about exactly how to fix that problem.
Another unrelated question. So can you change the prefix completely in a different location? All the install prefix?
Yes. Yes. I will also talk about that in the configuration section. So at this point, I'm going to turn it back over to Todd to talk about Spack's basic model.
And then back to you for config.